Hello friends, welcome to the first chapter of calculus. In this video, we will be learning and understanding some basic concept of limits from the absolute grassroot level in a very detailed manner. So we will not go into much more formal or bookish definitions. Rather, we will be using examples and diagrams to understand the concepts, and we will make our concepts clear in such a way that we can apply them effectively while solving problems. So let's start off with limits. Whenever in childhood we have learned arithmetic and mathematical operations, we have learned that division by 0 is undefined in mathematics. That is, we cannot divide any number by 0. So let us consider a function fx. This is a real valued function of x, where x is a real variable. This function is defined as x square minus 1 by x minus 1. And suppose our problem is to know the value of this function at the point x equal to 1. So if we want to know the value of this function from its definition at the point x is equal to 1, we cannot do it, because in that case the denominator will be 0, and division by 0 is undefined in mathematics. So the value of the function fx at the point x is equal to 1 is indeterminate. That is, we cannot determine it. So there may occur a situation where you may not know the exact value of the function at this point, but you want to make some idea of the value of this function at that point. So what to do in those situations? We will see that. So in this case, I remind you that some of us can make a mistake. That is, some of us can say that we can modify this function as, we can factorize this as x plus 1 into x minus 1 and x minus 1, and then cancel out these two, and then put the value of x as 1 and compute the value of the function. But that cannot be done, because when x is equal to 1, the value of x minus 1 is 0, and we cannot cancel out 0 and 0 in the numerator and denominator. So this is a very silly mistake. So remember and don't do this. So what to do then? In that type of cases, we apply a roundabout technique. That is, we take values of x as which are very close to 1 and try to observe that whether the values of fx approach any particular value or not. Here we are taking the values of x as 0.9, 0.99, 0.999. That is, we are pushing x closer and closer towards 1, but never making x equal to 1. So in that case, what we can see, I have computed fx by putting x in this using a calculator. You can do it yourselves and see. Whenever we put x is equal to 0.9, we get fx as 1.9. Whenever we put x is equal to 0.99, we get x equal to 1.99. For this value of x, we get fx is equal to 1.999. Again, all these are less than 1. Now we try to approach x from the greater side, i.e. that is from value which is greater than 1. Like take x equal to 1.1, we will get fx equal to 2.1. For x equal to 1.01, it is we are pushing x closer and closer towards 1, but never touching 1, never making x equal to 1. For 1.01, we will get this as 2.01. For 1.001, we will get this at 2.001. Now in both the cases, like in this case and this case, there is a common thing which you can observe. In both the cases, when you are pushing x more close and close towards 1, fx is moving closer and closer towards 2. See, 1.9, 1.99, 1.999. That is the difference between 2 and fx is becoming smaller and smaller. In this case also, when we are pushing x closer and closer towards 1, the values of fx are moving closer and closer towards 2. So in both the cases, as we push x towards 1, fx approaches the value 2. So after observing these kinds of phenomena, we will introduce the idea of limits, which is the basic of calculus, and you need to learn in a very detailed manner. Why I am telling this? Because we will be not doing limits only in this chapter, but in continuity also, in differentiability also, in the definition of derivatives also, and up to a certain extent in the last chapter, that is area under the curves or definite integrals area, that chapter also. So once you get hold of this chapter in a very well manner, you can apply the techniques in a very efficient way, it will be easier for you to understand the upcoming chapters. So we proceed to our next concept. So now we will understand what do we mean by the limit of a variable. So let us take that x is a real valued variable, okay, and a is a constant which is also a real number. So I represent the whole system by this diagram. As x is a variable on the real line, we take this real axis. Point A denotes this constant a on the real line. The point A1 denotes a plus 1, the point A2 denotes a plus half, the point A3 denotes a plus 1 by 3, and gradually it becomes closer and closer to a. Similarly, the point B1 denotes a minus 1, B2 denotes a minus half, B3 denotes a minus 1 by 3, and it moves closer and closer to a. Now for this constant a, we have got a representation in this diagram, but this x is a variable. So for this variable, we take a moving point which can move all along the x-axis, that is say p. P can move all along the x-axis. So p represents x in this diagram, and p represents x in this diagram, and this point a represents the constant a in this diagram. Now if this happens that p is starting from here, taking the value a plus 1 and approaching this point a like this, it crosses a2, it crosses the point a3 and comes closer and closer to this point a, but never touches the point a. So in our algebraic notations, what we can say, that x is taking the value a plus 1, a plus half, a plus 1 by 3 and coming close and close towards a, but it is never touching a. If this situation happens, then we will say that x tends to, this sign is pronounced as tends to, okay, x tends to a plus 0, or x tends to a plus simply this, or x approaches a from the right hand side. See, from our right hand side, if we face this side, from our right hand side, x is approaching the value a, but it never touches a. So we say x approaches a from the right hand side, or x approaches a from a larger value. You can take down as a note that what do we mean by x tends to a plus 0 or x tends to a plus. X is always greater than a. See, a plus 1, a plus half, a plus 1 by 3, and gradually it will happen a plus 1 by 4, a plus 1 by 5. Whatever value x takes, it is always greater than a, and it never becomes equal to a. And another thing, most important thing, this absolute difference, see, the absolute difference between x minus a will be less than epsilon. Here what is epsilon? Epsilon is a predefined small, can you see it? Oh yes, positive quantity. Okay, predefined small positive quantity epsilon. What does this mean? I will illustrate through an example. How much small epsilon you fix, we can make this absolute value of the difference between x and a less than that. Suppose you can fix epsilon as 1 by 10. Okay, and suppose our a is a. Now as x approaches from this direction towards a, at some point of time x can take the value a plus 1 by 20. Then what will be this absolute difference? This absolute difference will be 1 by 20, okay, which is less than 1 by 10. Again, you can take x more small, say 1 by 100. So at some point of time, as x approaches a from the right hand side, it can take the value x plus 1 by 101. Then what will be this absolute value? This absolute value will be 1 by 101, which will be less than 1 by 100. So you can see that how much small we take epsilon, that doesn't matter. This value, the modulus of x minus a, can be always made less than that epsilon. So in these cases, if this happens, we will say that x tends to a from the right hand side, and we will denote it by x tends to a plus 0 or x tends to a. Similarly, as p can approach the point a from the right hand side, it can approach from the left hand side also, or x can approach this constant a from lesser values of x. Like in the example we had taken in our first example, that x was approaching 1 from the lesser direction, that is we were taking 0.99, 0.999, and so we were pushing x towards a from a smaller number, and again we were taking the values of x as 1.1, 1.01, 1.001, and making x closer and closer to 1 from a greater direction. So in this case, what will happen? X will tend to take, x will approach the value a from a smaller side or from the left hand side, and in that case also x will never touch a. So that notation is x tends to a minus 0, or simply x tends to a minus. In that case, what happens? X is always less than ac, x is always less than a. X is not equal to a, it remains as it is. And here also the absolute value of x minus a can be made smaller than some predefined small positive quantity. Say if we again fix epsilon as 1 by 10, x can take the value 1 by 20. So what is the absolute difference? A cancels out. Absolute value of minus 1 by 20 is 1 by 20, which is less than 1 by 10. Again, if we fix like epsilon equal to 1 by 1000, take this as 1 by 2000. So this will be 1 by 2000, which is less than 1 by 1000. So no matter how much small you fix this epsilon, we will get a value of x at some point of time for which this absolute difference will be less than that epsilon. So this is what I mean by x tends to a from the right hand side and x tends to a from the left hand side. So there is a generalized version also, that is we can say x tends to a, just x tends to a when x can approach a from either direction, whether from the right side or from the left side. X can approach a from both the directions, that is as p is a moving point, p can move from this direction to this direction also, and this direction to this direction also. So it is denoted by x tends to a, or another notation that the limiting value of x or limit of x equal to a. In that case, x is not equal to a, And similarly, the absolute value of this difference, that is x minus a, is less than epsilon. Either you take from the left hand side or from the right hand side. That is, either you take x as smaller values of a, or you take x as larger values of a. We can always make this absolute difference smaller than some predefined small quantity epsilon. You need to know this meaning of this phrase tends to very well to understand the chapter limits. So we will move on to an example now. Now, if you have understood the meaning of x tends to a, then you should be able to tell that what do you mean by x tends to 3 or any constant. So the answer is very simple. X tends to 3. This notation means that if x takes value such that, if x takes value such that x is either less than 3 or x is greater than 3, but x is never equal to 3, and the absolute difference between x and 3 can be made even less than some predefined small positive quantity epsilon. This is what we mean by x tends to 3. X can approach 3 from either direction, that is from the left side also, from the right side also, but it never becomes equal to 3, and this absolute difference can be made less than some small positive quantity epsilon. This is what we mean by x tends to 3. So once we have learned what do we mean by limit of a variable, if I take say limit of a function here fx, what do we mean by this? It is very much similar to the limit of a variable. For x minus 3 less than epsilon, for this we mean that the absolute difference between x and 3 can be made less than some very small positive quantity epsilon. And if this happens, that is, the absolute difference between a function of x and a constant L can be made less than some predefined positive quantity epsilon. Let us take another symbol here, positive quantity delta. Then we will say that fx tends to L. The tends to notation is similar for all ax, f and fx. Nothing will change. So if this happens, we will say that fx tends to L, that is fx tends to take the value L. Okay, now we will be going to understand what do we mean by the limiting value of a function. Okay, so now we will learn that what do we mean by limiting value of a function. We don't often use the word limiting value, we use this word limit. So as x tends to a constant a, if this happens, the absolute difference between fx minus another constant L can be made smaller than some predefined small quantity epsilon, or it is equivalent to write fx tends to L. So I will not be explaining the meaning of the phrase tends to anymore. As x tends to a, if fx tends to L, say for x tends to a plus, that is when x approaches a from the right hand side, if we have fx is approaching a value L, then we write limit x tends to a plus fx equal to L, or the limiting value of fx is L when x tends to a from the right hand side. There is another notation LT, x tends to a plus fx equal to L. That is when x approaches a from the right hand side. If we see that fx is approaching a value L, then we write this. Consider our first example where we had when we are taking the values of x as 1.1, 1.01, that is x was approaching 1 from a greater value, that is it was approaching 1 from the right hand side, we could see that fx was taking the values 2.1, 2.01, 2.001, and fx was approaching L. So in that case we could have written limit x tends to 1 plus fx equal to 2. Similarly, x can approach this value a from the left hand side, and for x approaching a from the left hand side, if this happens, that is fx tends to L, then we will write limit x tends to a minus fx equal to L, or limit x tends to a lt x tends to a minus fx equal to L. Both these notations are commonly used. Here also we can consider our first example, that when x was approaching a from the left hand side, that is when it was taking values 0.9, 0.99 and moving closer and closer to 1, the values of fx were moving closer and closer to 2, like 1.9, 1.99, 1.999. So in that case we could have written limit x tends to 1 minus fx equal to L. Now we will be learning what do we mean by right hand limit, what do we mean by left hand limit, and what do we mean by existence of limits. So now we will study. So now we are going to study what do we mean by existence of limits. So let us first define two things, that is right hand limit, which is denoted by RHL, and left hand limit, which is denoted by LHL. So let us consider our previous model only, that x is a real valued variable and fx is a real valued function of x. So this quantity limit x tends to a plus fx, suppose this is equal to L1. So this L1, this is called the right hand limiting value or right hand limit of the function fx when x tends to a plus. If you call right hand limit, then you need not say that x tends to a plus, because when x tends to a from the right hand side, if fx approaches L1, then this L1 is only called the right hand limit. Similarly, when x approaches a from the left hand side, if fx approaches L2, another constant, this L2 is called the left hand limit of the function fx. And in general, if these two values are equal, then we can write limit x tends to a fx equal to L, where we can consider that L1 and L2 both are equal and it is equal to L, that is either x approaches a from the left hand side or from the right hand side, doesn't matter, fx will always approach the value L. Like in the first example we had when x approached 1 from the left hand side, then also fx approached the value 2, and when x approached the value from the right hand side, then also our fx approached the value 2. So in that case we can write limit x tends to a fx equal to L. So what is the condition for the function of the limit of a function to exist? The limit of a function fx is said to exist at the point x equal to a, where a is a point in the domain of fx, if I will write down three conditions. Those three conditions are satisfied, that is left hand limit exists, the right hand limit exists, and most importantly the left hand limit is equal to the right hand limit. If all these three conditions are satisfied, then only we say that the limit of the function fx at the point x is equal to a exists. And when we say that the limit doesn't exist, if any one of these conditions is violated, then we say that the limit doesn't exist. For our first example, we had seen that when x approached 1 from the left hand side, fx approached 2. Similarly, when x approached 1 from the right hand side, fx approached 2. So in that case, both LHL and RHL was equal to 2. So in that case, we could have written limit x tends to 1 fx. I am writing that function only, equal to 2. So now we will be clearing one of our confusions, that is, what is the difference between the limiting value of a function at the point x equal to a and the actual value of the function at the point x equal to a. So roughly I can tell that this is the limiting value and this is the value computed from the definition of the function. So I know this is not at all a convincing definition, so I will illustrate this through examples and not through definitions. Let us take a function, say fx equal to 4 minus x. Through examples your concept will be more clear, and we compute the limiting value and the actual value at x is equal to 4. We try to compute this. Now if we try to compute the actual value, that is f of 4, then we can easily do that. That is 4 minus 4 equal to 0. Now we try to compute this limit, that is limit x tends to 4 fx. So we check that whether the limit exists or not. That is, we first try to compute the right hand limit. What is this? Limit x tends to 4 plus fx is what? Fx is root over 4 minus x. So we have learned that whenever x tends to 4 plus, we'll write this. What do we mean? X is always greater than 4, okay? So whenever x is greater than 4, this quantity 4 minus x is less than 0, that is negative, and in the system of real numbers we cannot take a square root of a negative quantity, that is this right hand limit does not exist. And as this was the first condition of the existence of limit, so we can say that limit x tends to 4 root over 4 minus x does not exist. So in this first example, what we can see? We can see that we can compute the value of this function at the point x is equal to 4 directly from the definition, but the limiting value does not exist. So now we move on to the next example. Here we again take our first example, that is fx equal to x squared minus 1 by x minus 1, and try to compute both these values at x equal to 1. So we have done this many times, that limit x tends to 1 plus x squared minus 1 by x minus 1. It is when x is approaching 1 from the right hand side, this is equal to 2, and when x is approaching 1 from the left hand side, this is also equal to 2. So the right hand limit and left hand limit both are equal, thus we can write limit x tends to 1 x squared minus 1 by x minus 1 equal to 2. But in this case, if we try to compute f1 directly, it will be not possible because the denominator becomes 0. So in this case, this limiting value exists, but this actual value cannot be computed directly from the definition. So we further take another function. Let the function be defined like this: fx equal to 1 whenever x is not equal to 0, and fx equal to 0 when x is equal to 0. So we try to compute the limiting values. What is our left hand limit? Left hand limit is limit x tends to 1 minus fx. That is limit x tends to 1 minus we know that when we write x tends to 1 minus, we mean that x is less than 1, and we are trying to compute the value at x is equal to 0. So 0 minus. So we know that whenever we write x tends to 0 minus, we mean that x is always less than 0 and x is never equal to 0. So for x not equal to 0, we have the definition of the function as 1, and if we have a constant inside a limit, it is unaffected by this x, because x is a variable, it can go anywhere, but constant always remain a constant. And the right hand limit, if we try to compute 0 plus fx, in this case also x is always greater than 0 and x is never equal to 0, so this will be 1 and the right hand limit will also be 1. So the right hand limit and left hand limit both will be equal and will be equal to 1, but the limit of the function exists at the point x is equal to 0 and is equal to 1. But if we try to compute the functional value at x equal to 0, then from the definition we get f0 equal to 0. So we can see, even if here both the limit exists and this also exists, but they are unequal, so this may happen. So after seeing these examples, I think that you have been a bit convinced that these two are different things and these two are not always equal. Well, they may be equal. We can take a very typical example and show that they may be equal. So suppose we take fx equal to x square plus 2x in this case, and we try to compute that and the value at x equal to 1, both the limiting value and this value. So what will be our left hand limit? Left hand limit will be limit x tends to 1 minus x square plus 2x. So when x tends to 1, then what will x square tend to? X square will also tend to 1. You can do it in a calculator, or it is now, by now you should be habituated with this, that when x is tending to 1, x square will also become close and close to 1 square, and when x will move close and close to 2, 2x will move close, x will move close and close to 1, to either from the left hand side or from the right hand side. In this case it is from the left hand side, 2x will move close to 2, so here we get 3. If we compute the RHL, here x is moving towards 1 from the right, and for that also x square will move towards 1 and 1 square or 1, anything you can say, and as x approaches 1, 2x approaches to 2, so this is also equal to 3. So in this case the limiting value, the both right hand limit and left hand limit exists, and this limiting value is equal to 3. And if we try to compute the value of the function at x equal to 1 directly from the definition, then also we can do it, that is also equal to 3. So this is a very typical example where both the limit of the function exists at the point, and we can also calculate the value of the function from the definition at that point. There may be another case where this will not exist and this will also not exist. While solving problems, we will get many examples like that. So now we will be solving some problems with diagrams, because in many cases it happens that if you draw the diagram, it helps you to visualize the problem in a better way. So let us take a function fx equal to x square by x, and we have to determine its limiting value at x is equal to 0. So as we can see, this function is undefined at the point x is equal to 0, as in the denominator we have 0. So let us draw the graph. This is the origin. The graph looks something like this. this is angle 45 degree, this is also 45 degree, and it never touches the origin because it is the function is undefined at x is equal to 0. Now we draw this. Let this be LP. Let this point be L1, P1. Let this point be L2 and this point be P2. Let this point be L3 and this point be P3. Now you see that when x is at this point, the x value is at this point, then what is the value of fx? This height is the value of fx. When x comes here, what is the value of fx? This height is the value of fx. When x comes here, what is the value of fx? This height, L2 P2, this is the value of fx. For x, when x is here, L3 P3, this is the value of fx, and it gradually moves towards 0 but never touches 0. So we can see that as x is approaching 0 from the right hand side, the value of fx is decreasing, and almost disappearing, but never becomes 0 as it is undefined at x equal to 0. So as x approaches 0 from the right hand side, fx also becomes very small, that is approaches 0. Now from the left hand side, if you see, a similar case happens. At this point, say m1, this is q1, this m2, this point is q2, m3, q3, m4, q4. We can see that as x is approaching 0 from the left hand side, the values of fx, this is the value of fx, this is the value of fx when x is here, this is the value of fx when x is here, this is the value of fx when x is here, and gradually this height becomes very close to 0 as x approaches 0. So when x is approaching 0 from the left hand side, then also the value of fx, that is this height, approaches 0. So here we can see this is what? This is the right hand limit and this is the left hand limit. So in our case here, left hand limit is 0 and right hand limit is also equal to 0. So what we can write? Then we can write that limit x tends to 0, fx is equal to 0. We can solve another example in a similar fashion, that is by drawing a diagram. We take this function. We will find the limit at the point x is equal to 0. Clearly, what we can see that this function is also undefined at the point x is equal to 0, as we have denominator 0. So let us first define the mode function. It is x when x greater than 0 and minus x when x less than 0. We need not bother about the equality case here. Why? Because for the equality case, the function is undefined. So I write this function fx in a modified way. It will be 1 when x greater than 0 and it will be minus 1 when x less than 0. So here also I draw the diagram. The diagram will look like this. Now see, let this be a1 b1, a2 b2, a3 b3. According to the definition of the function fx, what is this value of fx? Fx is 1. So this point is 0 1. It never touches here because the function is undefined at x equal to 0. So we can see when x is here, the value of fx is this height, that is a1 b1, which is 1. This when x is at a2, the value of fx is then also 1. When x is at a3, the value of fx is 1. And as x approaches 0 from the right hand side, always the value of fx remains 1. That is, we can write limit x tends to 0 plus fx is equal to 1. And when x approaches from the left side, we can see that for every value of x, this point is 0, -1, the value of fx remains to be at -1. Whatever value we take as x on the x-axis, the value of fx will always be -1. Sorry, this will not touch as the function is not defined at x is equal to 0. So what we can write? We can write limit x tends to 0 minus fx. What is this value? This is -1. So what do we have? We have, this is our right hand limit, which is 1. This is our left hand limit, which is -1. So although right hand limit and left hand limit both exist, they are not equal. So in this case, we will see, or we will tell that the limit of this function at the point x is equal to 0 does not exist. Now we will move on to our next concept. In limits, these two are very important notations to know. What do I mean by x tends to infinity and x tends to minus infinity? Suppose x is taking values like this: 10, 10 square, 10 to the power 4, 10 to the power 8, 10 to the power 16, and increasing like this indefinitely. So how much large a number we can imagine x can take value larger than that? That is, x is increasing indefinitely and we cannot bound x in any way. So when x takes values beyond, larger than our imagination, or increases indefinitely, that is denoted by x tends to infinity. Similarly, if x takes values like this: -10, -10 square, -10 to the power 8, -10 to the power 24, and goes on increasing like decreasing like this, how much small a number we can imagine x can take a smaller value than that? That is, when x decreases indefinitely and can take a smaller value than our imagination, beyond our imagination, then it is denoted by x tends to minus infinity. You note that this x tends to infinity and x tends to minus infinity, these are just notations. Infinity and minus infinity does not denote any number. When we write this x tends to infinity, we mean that x is increasing indefinitely, and when we write this, we mean that x is decreasing indefinitely. At the same example, say fx equal to 1 by x, and put the values of x as 10 square, 10 cube, 10 to the power 4, 10 to the power 5, and so on. In this case, what will happen? The corresponding values of fx will be 1 by 10 square, 1 by 10 cube, 1 by 10 to the power 4, 1 by 10 to the power 5, and so on. That is what we can see. As we are increasing x indefinitely, the value of fx is moving closer and closer towards 0. In this case, we can write that as x approaches infinity, that is, when x increases indefinitely, the value of fx approaches 0. We can take another case. Take fx equal to e to the power x, where e is the Euler's number, that is a number lying between 2 and 3. Now we take the values of x as -10 square, -10 cube, -10 to the power 4, -10 to the power 5, and so on. In this case, we will need a calculator, and as I cannot calculate e to the power x, so what is the value of e to the power -100? We will see with the help of a calculator. It is like 3.72 into 10 to the power -44. So it is almost close to 0, and as we keep on decreasing x indefinitely, this will move more and more close to 0. So in that case, we will write as x decreases indefinitely, that is when x tends to minus infinity, the limiting value of fx approaches 0. So in this case, as you decrease the value of x indefinitely, the value of fx, that is the value of e to the power x, goes more and more towards 0. Now we will be giving some theorems, or you can call them properties, or you can call them formulas, which will help us in solving our problems. So now we will be learning something fundamental, limit theorems. These are also known as properties, or we will be using these as simple formulas. So I introduce x, which is a real valued variable. Fx and gx, these are functions of fx, obviously real valued functions. A is a real constant, L is a real constant, M is a real constant, C is also a real constant. So if we have limit x tends to a, I will not pronounce this many times, I will just say limit fx equal to L and limit gx equal to M. And if we have limit c fx, then as this is a constant, we can bring this out and write c into limit fx, and limit fx is L, so we can write this CL. And here suppose limit fx plus gx, we can separately calculate these two limits and then add them. That is, if there is an addition operator in the middle, we can separate the two limits and that value will be just L, the limiting value of fx and the limiting value of gx added. Similarly, we can do this for subtraction also. Limit fx minus gx will be limit fx minus limit gx, and this is be limit L minus M. Similarly, we can do this for multiplication also. We can separately calculate the limits and then multiply, and we can do this for division also, but there is one constraint or one condition for division, that is this limit must be not equal to 0. If this limit is equal to 0, then the value of this limit will be undefined or indeterminate. Now this is another property, that if we have limit x tends to fx equal to L and limit y tends to L, phi of y equal to phi of L, where phi is a function of real valued function of this variable y, where y is also a real valued variable, then this is a property of composition. Understand this carefully. Limit x tends to a phi of fx, then what we can do, we can bring phi out, put limit inside this, and as we know limit x tends to fx equal to L, this will be phi of L. Now suppose we have three functions fx, phi x and gx, and we know that limit fx equal to L and limit gx is also equal to L, and somehow the structure of this phi x is such complex that we are not able to find out the value of phi x or the limiting value of phi x where x tends to a, but we somehow can understand that or show that this inequality holds, that phi x always lies between fx and gx. Now if phi x always lies between fx and gx, and both fx and gx approach to the same limit, then we can write limit x tends to a phi x, this will be also equal to L. This theorem is known as the sandwich theorem, which you will study more elaborately in the undergraduate level. And now I will be stating last two formulas. The proof of those formulas are for the time being out of your scope. One is limit x tends to a. Learn these formulas carefully. This will be applied in a huge manner while solving problems. A to the power n by x minus a equal to n into a to the power n minus 1, where n is a rational number. N has to be a rational number. Okay. When x is tending to a, the value of this limit will be n into a to the power n minus 1. And another formula, limit x tends to 0, sin x by x is always equal to 1. In this formula, always remember that x is measured in radian and not in degree. For degree and radian, I can state the relation between them, that is 1 degree equal to pi by 180 radian. This is a very important formula. We will do a lot of problems with this, so remember these two formulas. The proof are not in your scope for the time being. If I get time, I will do the proofs for you. This proof for you, this is proof for undergraduate level. When in the UG level you learn Taylor's theorem, this proof will be easier, but I can give an idea how to do this proof. So today I end my class here. So see you in the next video, where we will be starting with problems and learn how to solve problems and apply these formulas.